Rotational dynamics. We start with Newton's second law for rotational motion. The net torque is equal to I times alpha. I is the moment of inertia, sometimes it's called rotational inertia. Alpha is the angular acceleration. Net torque is the sum of all the torques acting on a rotating body. The question is, how do you find this I? For a discrete mass distribution, we can easily find I, which is sigma times mr squared. And the units of I are kilograms times meter squared. Let's go over an example to see how to find the inertia of a mass distribution, this discrete mass distribution. Two masses, 2 kilograms and 3 kilograms, are connected by a light rod of length 4 meters. The rod is free to rotate about an axis perpendicular to the rod at the center. Find the inertia of the rod. A 4 Newton meter torque is applied on the rod. What is the angular acceleration of the rod? So it's important that the question says the rod used to connect the two masses is a light rod. So we can ignore the inertia of the rod. So we only consider these two masses. So our formula for the inertia is I equals to sigma mr squared. So we sum these mr squared terms. Let's assume that 3 kilogram mass is m1 and 2 kilogram mass is m2. So it's m1 r1 squared plus m2 r2 squared. r1, r2 are the distances to the masses from the rotational axis. They are not vectors, so you don't have to consider the direction. It's just the distance between the rotational axis and the masses. So R1 is 2 meters, R2 is 2 meters as well. So it's 3 times 2 squared plus 2 times 2 squared. It's 20 kilograms times meter squared. So the angular acceleration is net torque divided by the inertia. The net torque is given as 4 Newton meters in the question, and we found the inertia, which is 20 kilograms meter squared. So 4 divided by 20, that's 0.2 radians per second squared. Now this is the second example. Find the answer to A and B in the previous question if the axis is perpendicular to the rod at the center of the mass of the 3 kilogram object. New rotational axis is going through the center of mass of the 3 kilogram object. The previous we had the axis through the center of the rod, but now it's a different rotational axis. Now we will see whether it would make any differences to the answers we got. Now let's find the inertia again. Sigma mr squared, that's m1 r1 squared plus m2 r2 squared. So the main difference is now r1 is 0 because distance to the axis from m1 is 0. So the first term is 0, and m2 is 2 and r2 is 4 meters now. So it's 2 times 4 squared, which is 32 kilograms times meter squared. So the inertia has changed. So inertia is not like mass. It changes with the rotational axis. So the rotational axis is important. So the new angular acceleration is 4 divided by 32, which is 0.125 radians per second squared. Example 3. Find the net torque exerted on a dual pulley system and the angular acceleration. The moment of inertia of a pulley is given by 1/2 mr squared. The radii of the pulleys are 10 centimeters and 20 centimeters. M1 equals 0.5 kilograms and M2 equals to 1.5 kilograms. So this is the dual pulley system. The smaller pulley has radius 10 centimeters and the larger pulley has radius 20 centimeters. The smaller pulley has mass 0.5 and the larger one has mass 1.5 kilograms. And then there is a force on the smaller pulley, which is 30 newtons, and there is a force on the larger pulley, that's 25 newtons. So first we need to find the net torque. So the torque is the force times the lever arm. So that's force is 30. But in this situation, we know that the radius is the lever arm because this force is always perpendicular to a line joining the point that force exerted on the rod with the center. So this is always, normally for a pulley, the torque is radius times the force. So we use that here. 25 times R2, that's for the larger pulley. 25 times its radius, that's the torque on the larger pulley. And also we need to consider the sign. So this 25 Newton force makes a rotation in the counterclockwise direction. So that's the positive torque. And the 30 Newton force make a rotation in the clockwise direction. And that's why we have 25 times R2, which is positive, and 30 times R1, which is negative. So it's 25 times 0.2 minus 30 times 0.1. So the 2 Newton meters, that's the net torque. To find the angular acceleration, we also need the total inertia. Since we have two pulleys, the total inertia is the sum of the two inertias. So that's I1 plus I2. So 1/2 m1 r1 squared plus 1/2 m2 r2 squared. So there is an extra 1/2 here, so we don't need that. So let's delete that. Okay, so it's 1/2 times m1 r1 squared plus m2 r2 squared. So now it's right. 1/2 times 0.5 times 0.1 squared plus 1.5 times 0.2 squared. That's equal to 0.0325 kilograms meter squared. That's the total inertia. Then the angular acceleration is the net torque divided by the total inertia. So 2 divided by 0.0325. So it's 61.5 radians per second squared. Now we will go over a bit harder question. We did a similar question previously without considering the mass of the pulley. As an Atwood's machine, if you go back to Atwood's machine and see how we did that, we didn't consider the mass of the pulley. We ignored. We said that it's negligible, and then we found the acceleration of the Atwood's machine. Now here we revisit the same problem, but we consider the mass of the pulley. So that makes a big difference here. The biggest difference is when you consider the mass of the pulley, then the tensions on the string are not equal. Tension T1 and tension T2 are not equal anymore because you need some torque to rotate the pulley, and that torque makes a difference to the tension on either side of the rope. So the question is, find the acceleration of the following system. The mass and the radius of the pulley are 2 kilograms and 20 centimeters respectively. What are the tensions of the rope? I is given by 1/2 mr squared, and ignore frictional forces. And also we ignore the mass of the rope. We still assume that the rope is very light. Now first we need to draw the free body diagram. For a problem like this, we need free body diagram for each moving object. So we have two masses, so we need two free body diagrams for the masses, and then we have a pulley which is also a moving object, so we need a free body diagram for that as well. So you have three free body diagrams. So the masses are moving along straight lines, so they are linear motion. We use Newton's second law. But the pulley is a rotational motion, so we use the Newton's second law for the rotational motion, which is net torque equals I alpha. Now for the 5 kilogram mass, we can use Newton's second law. F net equals to ma. So F net is T1 minus 5 times 9.8. That's 5 times negative acceleration. So we put minus a because acceleration is downward for the 5 kilogram block. So it's a negative value. So we put the negative sign there. So we can simplify that. We get T1 equals 49 minus 5a. So let's consider that as our first equation. We repeat the same thing for the 3 kilogram mass. F net equals 2 ma. So T2 minus 3 times 9.8 equals to 3a. So T2 equals to 29.4 plus 3a. So the difference here is acceleration is positive in the second equation because this block is moving upward, so it's a positive acceleration. For the pulley, we use tau net equals to I alpha. The tau, there are two tensions. As I said in the previous question, the torque is tension times the radius of the pulley. So the torque by tension T1 is a positive torque because it's counterclockwise, and the torque by tension T2 is a negative torque because it's a clockwise rotation. So T1R minus T2R equals to 1/2 mr squared times alpha. 1/2 mr squared is the inertia which is given in the question. And here again we need to think about the direction of the alpha. We assume that 5 kilogram mass is going down, so that means the pulley is rotating in the counterclockwise direction, so the acceleration is also in the counterclockwise direction, so that's a positive acceleration, so we don't need any negative sign there. Then it becomes T1 minus T2 times R equals to mr squared alpha over 2. Now we can cancel 1 r from the equation, so it becomes T1 minus T2 equals to mr alpha over 2. This equation doesn't have a, it has alpha. The other two equations have a. To solve these equations, we need a in the equation. So we can do that because alpha is a divided by the radius, or the angular acceleration is equal to linear acceleration over the radius. So by substituting this value, we get T1 minus T2 equals to mr over 2 times a over r. You can see that this r cancels from the equation. So we end up with T1 minus T2 equals to 2a over 2, that's a. So T1 minus T2 equals to a. So that's our third equation. By substituting 1 and 2, we get 49 minus 5a minus 29.4 plus 3a equals to a. By simplifying the equation, we get 19.6 equals to 9a. So a equals 2.18 meters per second squared. So that's the acceleration of the system. And we can find T1 from equation 1. And that's 49 minus 5a, so 49 minus 5 times 2.18, that's 38.1 newtons. And T2 equals to T1 minus a, that's 38.1 minus 2.18, that's 35.9 newtons. So at this point you can see T1 and T2 are different. In the previous time, we assume they are equal because we ignored the mass of the pulley. They are close, but they are different. Okay, if the mass is very small, you will see they are approximately equal. So the angular acceleration alpha is a divided by the radius, so it's 2.18 divided by 0.2, so that's 10.9 radians per second squared. The last part of this section is rotational work and rotational energy. Rotational work is defined as rotational work equals to tau times theta. Tau is the torque and theta is the angular displacement, which must be in radians. And rotational kinetic energy we define as 1/2 I times omega squared. It's similar to 1/2 mv squared. So we replace mass by the inertia and we by omega. So this is the rotational kinetic energy. The idea is a rotating body has a rotational kinetic energy. So in general, any moving object has a rotational kinetic energy and the linear or translational kinetic energy. Example 5. A marble is rolling down an inclined plane. The speed of the marble at the top of the plane is 5 meters per second squared. Find the speed of the marble at the bottom of the plane. The inertia of the marble is given by 2 over 5 times mr squared. You need to write the mechanical energy at the top of the plane, which is mgh0 plus 1 half mv squared plus 1 half I omega squared. So this is the rotational kinetic energy, and this is the translational kinetic energy. At the bottom of the plane, mghf plus 1 half mv squared plus 1 half I omega f squared. So then we can substitute I, which is 2 over 5 mr squared, at both places. So once I is substituted, we can divide the equation by m. So m is not necessary to find the final speed. So we get this equation gh0 plus v0 squared over 2 plus r squared omega 0 squared over 5 equals to GHF plus VF squared over 2 plus R squared omega final squared over 5. But still we have V0 squared and omega 0 squared in the equation, and on the other side we have V final is squared and omega final squared. So our idea is to find the final speed. So we need to substitute this omega by V. We know that V is equal to R times omega. So omega is V over R. So by substituting that, we get GH0 plus V0 squared over 2 plus R squared over 5 times V0 squared over R squared equals to GHF plus VF squared over 2 plus R squared over 5 times VF squared divided by R squared. Then you can see that this R squared cancels with that R squared, same way here. So there is no R term in the equation. So the equation simplifies to GH0 plus V0 squared over 2 plus V0 squared over 5 equals to GF plus VF squared over 2 plus VF squared over 5. We can add these two terms and we can add those two terms as well. So it becomes GH0 plus 7 over 10 V0 squared equals to GHF plus 7 over 10 VF squared. So now we can plug the values given in the question. H0 equals to 2 meters, HF is 0 meters, and V0 equals to 5 meters per second. So the plugging those values, we get 9.8 times 2 plus 7 over 10 times 5 squared equals to 0, because HF is 0, plus 7 over 10 times VF squared. By solving the equation, we get VF equal to 7.28 meters per second. Example 6. A cylinder of radius 20 centimeters rolls along a flat horizontal surface at 8 meters per second. The mass of the cylinder is 6.4 kilograms. Find the translational kinetic energy, rotational kinetic energy of the cylinder. The rotational inertia of the cylinder is given by I equals 1 half mr squared. So the translational kinetic energy is 1 half mv squared. That's the regular kinetic energy, which is 1 half times 6.4 times 8 squared. That's 204.8 joules. The rotational kinetic energy is 1 half I omega squared. So it's 1 half times 1 half times mr squared times omega squared. Here again we need to substitute omega by v. So omega squared becomes v squared over r squared. So then r squared cancels here. So mv squared over 4, that's 6.4 times a squared over 4, this 102.4 joules. So the total kinetic energy of the cylinder is this value plus that value. So total kinetic energy is the sum of the translational kinetic energy and the rotational kinetic energy.